Hello, welcome all. So in the previous lecture we have studied about the local gradient induced error of neural network. We have seen that the uh, output error or output if a neuron is in the output layer. So how can we determine the local induced error with the help of that neuron? So the equation of the local induced error delta j will be becoming in the form of the overall error in the network and the incoming inputs of that neuron j. So from there we can see that uh, if a neuron is in the output layer, so for output layer the equation of delta j would become the error of j in it that produces the error, and the activation functions first order derivative that we have already known, that is also the incoming inputs of the transfer function. So in this portion we computed the delta j, and for the output layer neurons connected with the previous inputs is being updated with the help of the equation of delta wji, which is nothing but less of the learning rate eta delta j, that is being local induced error. It is being called as local induced gradient of neuron j, and the incoming inputs from the yi. So that was being designated for the equation when the local inducer, when the jth neuron is in the output layer or in the output contour. So if the jth neuron is considered as a hidden neuron, then what will happen? Then the local gradient for the neuron j is recursively determined in terms of the local gradients of all neurons to which neuron j is directly connected. For example, if we are saying that this is the output layer, it has three nodes, that is can be considered as k layer, the output layer, and in before that there is a p layer. It is being considered as a hidden layer, and it has four nodes, and in before it has a jth layer, it has three nodes, and this is jth layer. To compute we can suffix it j1, j2 and j3, p1, p2, p3 and p4, k1, k2 and k3 to suffix this network. If it is considered as a fully connected neural network, then the connections of from j is being denoted as there is a fully connections between the 3 and 4 layers. And it also for example, if p1 is connected with only k1 and k2, and p2 is connected with k1 and k2, and p3 is connected with k1 and k2, and only p4 is connected with k3. So we just consider this as a network. It's not a fully connected network, but we are showing the connections of the network, where k layer is the output layer and j is the one of the hidden layers that we are trying to consider, or we are trying to compute the hidden local induced error. So for that, if we consider delta j1, it might be dependent upon, it is called that recursively determined. So we are calling a recursive function called r. It's a recursive function r, which is fully dependent upon the connections that j1 is having with the p layers. That means delta of p1, delta of p2, delta of p3, delta of p4, and just for simplicity, p1 is connected with some recursive function that is being told as k1 and k2. So it is being replaced with the p1. So first the k1s will be computed, and delta k1, we already know what will be the value of delta k1. Delta k1 will be simplified. Delta k1 is nothing but less of error of k1 and phi prime of vk1. That is called the output layers computation. So delta k will be replaced in the recursive function, and some computations will be performed in the recursive function, and for that it will be gone to the upper layers. So the main concept of this portion is the hidden layer neurons must be connected with the proper must be connected to the other layers, and which helps to compute the local gradient is the direct connections that the current hidden neuron is having with the next layers. So the computation will come from the output layer, and it will be propagated back towards the connections being connected with the hidden layers. So let's move on in the further, and let's see how much more we can collect information from here also. So let's see the picture, and we consider there is two neurons currently we are actually depicted or inspecting. So the output layer neuron is being considered at here. The kth neuron is being considered as the output layer neuron, and this neuron is being considered as the hidden layer neuron. So output layer neuron and the hidden layer neuron both are being considered here. So for the output layer neuron, what we can have the equations, we have already known that delta k of this output layer neuron can be considered as ek and phi prime of vk. Okay, so what is phi of vk means? Phi of vk is nothing but the output of yj, right? Phi prime of vk is output of yj? No, I think so. So phi prime of vk, that means the activation function, that is called the vk. So it must be the output of yk, right? And what will be the error of k? Error of k is nothing but the dk minus yk, right? Okay, so these are the norms equations that we have already seen, just the change of the subscript. So we must be acquainted with these things in a very well manner. So for that, this is what we currently actually focusing is local induced error, delta k. So delta k is producing the ek phi prime of vk. Phi prime is considered as the activation function, and the output it generates is ek. So overall error might be optimized with the help of ek. So for the hidden layer neuron, our main goal is to compute the delta j. So how can we compute the delta j? So let's figure it out. We can rewrite the delta j as the overall error of the network. The incoming input set is, for example, we know from the equation of the local induced error of delta j is being rewritten as delta e of delta vj, right? It's correct. So by the chain rule, we can define delta e with the help of delta yj. Delta yj will be defined by delta vj. Okay, from here you can also see the circular portion, that how the overall error will get reduced or will be dependent upon the value of yj. So yj is also dependent upon the vj. So we can say yj is differentiable with vj, and it can be represented with the help of chain rule. Okay, so from here we can say delta of yj by delta of vj can be rewritten as the activation function of the derivative of phi prime of vj. So we can call it with a generic term that this is the first order derivative with the help of vj. So we can say phi prime of vj is the portion of delta yj and vj, and it can be replaced with the help of this equation and can be represented as phi prime of Vj. Okay, so now what we need to compute is the portion is in here, delta E of Yj. So let's try to compute this with help of delta E by delta of Yj. So let me just clear up the screen a little bit, but we need those equations. So we need those equations in our manner. So what we can have, delta E of Yj. So this is our computation. So for the respect, we can rewrite that En, we remember the average energy is half of where the contour of the output layer is k, Ek square of N. This equation we have familiarized with. We have seen this equation in previous loss function. So the error here, so we want to compute the delta E of delta Yj. Okay, so there is summation of contour of C can be rewritten as, if E, you can consider this Ek. Okay, so there is Ek and delta Ek with respect of delta of Yj, right? So we can rewrite this equation in terms of here. Where is the half goes? The 2 into half is multiplied and it is cancelled out and 1 is represented. So the overall equations is turns into Ek and delta Ek by delta Yj. Why k is terms is because this j is connected with multiple k's. So we cannot consider the other cases is as constant and chunk out as 0. So that's why the summation is still remaining, because we don't know how many k's it connects with the j, current j. So that's how we are going to represent this equation. So let's consider it. Put a minus sign here in the up front, and there is a k belongs to C Ek, and put a minus sign with delta Ek by delta of Yj. Okay, let's chunk it down a little bit. Why I actually getting delta Ek and delta Yj and a minus sign? So from the upper equation we can see Ek that can be represented as delta Ek and delta Yj, that can be represented as minus delta Ek of delta of V. This is Ek. So Ek is dependent upon Vk. Okay, so transformation of Vk. So Vk we will rewrite. Okay, and for that the Vk, it is dependent upon somehow by Yj. So we can say delta of Vk is delta of Yj. So we can say that in terms. So why this minus sign comes? Because this minus signs can show up that Ek, this delta Ek and delta of Vk, what it shows that it might have the equation k belongs to C Ek, and this can be rewritten as phi prime of Vk. Okay, this portion can be rewritten as phi prime of Vk, and from here this portion can be rewritten as W of Kj. This portion can be represented as W of Kj, because Vk is a representation of W of Kj Yj, right? Where k belongs to 0, k equals to 0 to m. Okay, so can be represented, and if you differentiate with Yj, the Yj term will vanish and only Kj term will be represented. The others are being constant in manner, what we have already been seen. So it can be rewritten as delta Vk with respect of delta Yj will always turn into Kj. Okay, So that's from that the wkj belongs to here. And for delta yk, delta ek and delta vk, the ek portions is being denoted as delta of if you put the -1, then it is being rewritten as delta of dk minus yk and delta of vk. There is some minus here, and with the help of dk minus minus will be gone, so dyk will turn into dvk. So dyk in turns into dvk. So from here we can say the yk and vk part, the yk and vk, it can be represented as the phi prime of vk, because yk is nothing but phi of vk. So delta of phi of vk with respect of vk will turns into the first order derivative of phi prime of vk. So the overall equation, it comes up from the overall equation, it comes up into the hand of delta of e, delta of yj is nothing but else, if you put the minus sign here, where we are actually computing with the minus sign, so if so without the minus sign it will be minus sum of k belongs to c, ek and phi prime of vk will turn them into the value of dk and multiplied of kj. So the dk will produces the local induced error of the output layer, local induced error of output layer, and wkj is none but less the connection of the connected output layer with the incoming inputs. So wkj is the weight associated directly connected with the jth layer to the kth layer. So we are considering the jth layer with the kth layer, so that's why we are actually saying that wkj. And the default minus will be conjugated or will be defaulted, and that's why the current equation will comes up into the k belongs to c delta k wkj. So the overall equation that turns up now is for the output layer, the delta k is none but less of ek phi prime of vk, and if it is considered as output layer, and if it is a hidden layer, then delta k is none but less the summation of, where we can say that considering the jth layer, so delta j is ej and phi prime of vj, and if hidden layer is j and the output layer is considering a kth layer, so delta k and w of kj, that means connected directed with the layer that is being connected with the jth layer. So this is the chain rule that we have already seen. The delta j is equals to the delta minus delta yj. The equations are being formed in the manner, and how the chain rules has been depicted, that has been shown up here, that the delta j is being chained as delta e by delta yj, and delta yj is being denoted as delta of vj. And what if delta of yj is delta of vj equals to phi prime of vj? Okay, so that is being shown up here. Okay, so now en equals to half of ek squared, that is being comes from the signal, the average signal in the portion. Okay, the average signal of the portion minus delta e by delta yj is in the first order derivative of delta e by delta yj equals to minus of the ek delta ek by delta yj. That is being denoted as the derivative of this upper equation. So the upper equation will compute, and that after that the ek will be denoted as delta ek by delta vk, and delta vk of this portion is being comes up with the help of a chain rule that it is being yj, so it can be rewritten as a function of delta vk and delta vk, and this portion can be cancelled out. So the chain rule helps us. From there we can change that this portion can be called as the activation function, and this portion can be computed as the w of kj, because vk is none less kj and yj. Okay, so that's why delta of vk of delta of yj is denoted as w of kj. So from there we can obtain that delta k is equals to w of k. Okay, so from here it is being suffices. Okay, so now let's move on to the next, that local gradient of a neuron j, how it's actually translated. So local gradient of neuron j delta j, we can say that phi prime of vj is being multiplied with the help of delta k and w of kj. Okay, so we can say that because as delta k and w of kj is being multiplied with the activation function of vj. Okay, and that's how the rule of the thumb is being set up. Okay, so because delta j is computed with the help of phi prime of vj, so this portion is being multiplied, so phi prime of vj is already chunked out, and this portion will generate as the delta k of wkj. So that's why the delta j is being denoted as in here. So this portion is the correct equation of computing the hidden layer node. Okay, so delta ji, and this is the weight update delta rule that we have already seen, the weight update delta rule. So according to the weight update delta rule, if neuron j output neuron has been considered, so there will be an activation function's first order derivative multiplied with the error, and also if the hidden node is there, the activation function of the first order derivative of the current hidden neuron is multiplied with the connected output layers induced error with associated with the average weight of the associated with the weighted sum of the connected kth layer. So C in here is considered as the following layer, one containing the J. That means the direct connections that C is having with the connections with the hidden layer neuron of J. So we can elaborate the equation with the help of the activation function elaboration as well. If we consider A is greater than 0, then we can rewrite this equation again with the help of the activation function being decomposed with the help of its own function and its activation function, and the derivative of the activation function can be decomposed with the help of its of its own and its inverse function multiplication. So the equations are being shown here as well, where this dkj, that means the desired training output of the kth layer, and j means the jth neurons output. So in the back propagation, so we have two different phases. So what phases that the computation will compute? They run the neural network and compute the error. So in the phase where we computing the error and forwarding the signals from input layer till output layer is being considered as the forward pass. Each neuron of the output layer that error is being computed is called the forward pass. The backward pass is start at the output layer. Loss function gives how much loss this forward pass is being generated. Okay, so the error the backward pass starts with the output layer and pass the errors backwards through the network. That means it is passing the information, error information, from the output layer to the previous layer and the previous layer and the previous layer. So layer by layer it is actually passing the information by recursively computing the local gradient of neuron. So the word here is important is why recursively, how recursive computation works. So we know that the recursive computation is being computed in the depth layer and it is returning the results in the upper layers. So as it is, the backward pass also try to compute it like this way. Okay. So far the recursive computation has been performed and the local gradients of each neuron is being computed backwards with the help of the recursive computation, and the current jth neuron is being computed with the help of in the backward pass. So in the backward pass there are some two computations has been performed. The local gradient of this computation of the multi-layer perceptron computation signal flow of forward pass, and what is happens in the backward pass that is being denoted in the equation in the bottom. Here in the bottom the backward pass is being denoted, and in the front this is being considered as the forward pass. This is forward pass and this is actually number placed, it is backward pass. So far that is the equation that we are actually trying to compute the local gradient inputs and the output of the signal flow. Thank you so far. Okay, now we can see a sample example of hidden neuron computation. So this is a sample example. In here we can see that there is a jth layer in a hidden layer. We can consider it as a hidden layer. The output layer is being considered as a k layer. So k1, k2, k3. There are 3 nodes in the output layer, and there are some nodes with p1, p2, p3 and p4. These are also hidden layer, and they are connected with the another hidden layer that is considered as in J. So our main target is to compute the jth layer hidden neurons, and how we can compute it with the help of the connections that we are having. So let's just cap with the connections that currently K1, K2, K3 are connected with the P layers, and the P layers are connected with J layers. So J1 is being connected with P1, P2, J2 is connected with P3, P4, and J3 is connected with P2, P3. So this is not a fully connected neural network. These are connections we are showing that how the recursive computation might happen where the hidden layer neuron local induced error is being computing. So the P1, P2, P3 is connected with P1 is connected with the output layer K1, P2 is connected with the output layer neuron K2, P3 is being connected with 2 neurons K1 and K3, and P4 is being connected with K3 only. So for the output layer we can easily rewrite the local induced error with the help of activation functions, and the error computed from the kth outputs, that ek1, ek2 and ek3 is being multiplied and being integrated with the local induced error of delta k1, delta k2, delta k3. So the induced error is being computed inside the cell. So these are being considered as delta k with the help of suffix. This is considered as delta p with the help of suffix, and this is considered the delta j with the help of suffixes. So in this way we can compute the equations. So for that we have to compute the delta p's first. So because without the delta p you cannot have the result of delta j. So let's compute the delta P1 first. The delta P1 is very easy. It is directly connected with K1. So delta P1 is being computed in a manner it's like phi of activation function of P1 that is being currently computed in the P1 cell. It is being multiplied because it's only connected with 1. We can avoid the summation sign and we can rewrite it as delta K1 multiplied with W of K1, and the jth neuron is being considered as P, so it will be considered as P1. So delta K1 and P1. P1 node is connected with K1 node, so delta K1 and P1 is being connected with the associated weight of delta W K1 P1, and delta K1 is being computed in here. So in this way the delta P1 is being computed. And what about the delta P2? If we consider the delta P2, it is also connected with K2 directly, so we can say the activation function of VP2 delta K2 and the summation of K2 P2, right? This has been considered as the portion of the connectivity of delta P2, the local coordinate. What about delta P3? P3 is connected with K1 and K3, so well, now we can have the summation. So the phi prime of VP3 delta, and the delta 1 will be now considered as the summation of K1 and K3. So we can say, we can add it in a different way, so we can say it will be delta K1 and K3, so delta K1 W of K1 P3 plus delta K3 W of K3 P3. So this is the equation of delta of P3. And next, if we can move forward, delta P4, the P4 term, the P4 term is being considered with K3 only, so we can say that phi prime of V P3 that is being computed with delta K3 W of K3 P3. Sorry, it will be not P3 because it's connected with P4, so it's P4. So these are the equations that is being formed with help of P, but our target is to compute the jth layers. So how we can compute the jth layers is being now very easy. So that if we can say, we are going to say that J1, so J1 is connected with P1 and P2, so you can rewrite the equation at phi prime of V J1 multiplied by, this is being multiplied with the help of two portions, so it is delta P1 with W of P1 and it is being connected with J1, right? So delta P1 W of P1, and it is being connected with J1, so it is being rewritten as here, and plus this is being sum up because it is being connected with two P, let's see, P1 and P2, so it is being connected with P1 and P2, and it is being rewritten as J1. Okay, so the connectivity of the equation is being shown here, and we can elaborate it a little bit more how it is connected with recursively. Thus delta P1 can be rewritten as phi prime of Vp delta K1 W of K1 P1, and this being whole multiplied with the equation of the associated weight of delta P1 and J1. and this is being added up. Delta P2 can be rewritten as phi prime of Vp2. The subscripts portion need to be clearly defined, P2, and let's rewrite the plus equation in a manner in here. Phi prime Vp1, this is 2, and it is being multiplied with delta K2 W K2 P2, and this is being multiplied with the associate weight of W P2 J1, and this is being added up with this one, and then they are being multiplied with phi of Vj. So thus the J1 is being recursively computed with the help of K. So we show the J1 options, and you can sufficiently show that J2 can be rewritten in the manner of Vj2 with the help of, see the connections P3 and P4. So we can say that P3 and P4 belongs to Pi, and you can say that delta of Pi is being connected with the help of Pi and multiplied with J2. So this can be rewritten also as with the help of delta of J2. This is another short form rewritten as in the context of compute. So these are the overall scenario how the backpropagation computes the local gradient of induced error inside the cell. So this is the overall picture how you can compute a local induced error with the help of the gradient, and can compute it with the proportion of the delta of J2. So thank you very much for having it in the having the portion. I hope you all understand how you can compute the hidden layer portion with the help of delta J2.